Throughout the world, in millions of landfill sites, there are literally billions of Lambda sensors, the oxygen sensors, used in these cars and all modern cars to set the fuel-air mixture, that have been thrown away for no reason at all. You could go back again, pick them up, put them in your car and they'd work perfectly. And I'm going to explain the reason for that. Now, most Lambda sensor errors aren't anything to do with the Lambda sensor. It's very like saying, well, my car had lots of steam coming out of it, it's cooling all over the place, the temperature gauge went into the red. What I'm going to do to fix that is change the temperature gauge, because that's obviously where the problem is. Yeah, it's the same thing with the Lambda sensors. They'll tell you there's a problem, you change it, it's going to make no difference at all. Of course, all this theory is a great waste of time unless I show you exactly how to fix the problems. So yeah, we're going to be opening the bonnet, getting the engine covers off and having a look. I'm going to show you exactly how to fix it. Okay, so this video has been brought on by a raft of posts on BIMA forums and on the other forums that always go the same way. Done diagnostics on my car because it was running a bit lumpy, gave me a Lambda sensor error. I've changed that Lambda sensor, it's made absolutely no difference at all. Car's still running lumpy and I've got the same Lambda sensor error. Is this another faulty Lambda sensor? No, it's not. And I'm going to tell you why it isn't and how to fix it. Now, if you're just interested in finding out what the problem is, well, go to the end of the video. I'll put chapters in on it and I'll explain what other problems cause those faults. But if you want to know how Lambda sensors work down to the atomic level, yes, that's how far we're going today, right down to atomic level, how they're made, what can go wrong with them, because they do go wrong sometimes, but very rarely. Yep, we'll explain all of that. So get yourself a nice cup of tea, settle down. This video is going to be long and complicated. That's the way we like them. Let's get on with it. Welcome to Timm's BMW Repairs and Information. Right, before I talk, I will warn you that there is live firing going on at the ranges just over there. So we might be interrupted now and again. Don't worry about it, they're pointing that way, we should be all right. Okay, yeah, off they go, yeah, large caliber by the sound of it as well. Here's a question for you, what are Lambda sensors for? Why were they introduced into the modern cars? Well, the normal answer I get is, well, they are there to set the 14.7 to 1 fuel-air mixture to get the best performance and economy from the engine. Well, that's not true, although that is a byproduct of it. The second answer I usually get is, well, they're there to protect the catalytic converters. If it's too lean or too rich, then the catalytic converters are damaged. Yes, that is true, but it's also another byproduct of the primary reason you've got Lambda sensors, and that is to ensure the catalytic converters convert noxious gases to harmless gases. And they only do it with a certain amount of residual oxygen. They need that oxygen for the conversion process of noxious gases into clear gases. So that is their purpose. Now, the Lambda sensors, the narrowband ones in here, are designed by the amount of doping they have in the zirconium to flop over at 14.7 to 1 fuel-air mixture. But let's be perfectly accurate here. It's not the fuel-air mixture they're interested in. It's a difference in concentration of oxygen from the outside world to that in the exhaust pipe. And that is their primary and only purpose. All the other things that happen, like economy and the catalytic converters lasting a long time, are all byproducts. Its most important function is to ensure the catalytic converters convert noxious gases to clear gases. There's two different types of Lambda sensor, narrowband and wideband. Now, in my ancient E31, which is 25 years old now, it's got a narrowband sensor. Think of them as a digital measurement. Too lean, you get a 0, too rich, you get a 1. That's what narrowband sensors are all about. Now, I know people are going to say, well, they are an analog sensor. Yeah, but the band is so small between too rich and too lean. Just think of it as a digital sensor. And I'm going to explain exactly how they work in a minute. Now, as I said, old cars like my E31 has 2 oxygen sensors, 1 for each bank. Doesn't have any more sensors behind the catalytic converters. Now E38s and E39s, which used a later model engine, the M62 TUB, technically upgraded ones, ended up unfortunately with 4 Lambda sensors. 2 for each bank, so it's got 1 in front of the catalytic converter, it's got 1 behind, and the same on the other bank. The ones behind the catalytic converter don't measure fuel-air mixture. They are there, don't have anything to do with the engine control, they are there to check the catalytic converter is working correctly. And if they get plugged or they melt, then it knows, and you'll get a warning that the catalytic converter has failed. That comes from that Lambda sensor. So error codes to do with failed catalytic converters are from the rear sensors. Now, I didn't get any on my E31 or my E32 or my E38s, had quite a few of them, apart from the last one, which was a TUB. And of course, we've got them now after the catalytic converter on more modern cars like my 6 Series, my E64. Forget about the downstream ones, that's what they call them, downstream of the catalytic converter they mean. They don't have anything to do with fuel air mixture. We're not interested in them at all. It's the ones in front. Now the ones on the more modern cars like my E64 are wideband sensors. They can tell you what the fuel air mixture or the residual oxygen is to a reasonable degree of accuracy. Whereas the one in the older cars, E31s and all the rest of them, narrow band, and such a narrow band that it can't tell you if it's 14.7 to 1. Only tell if it's slightly richer or slightly leaner. Okay, so we've got to this point where you have a 14.7 to 1, good for catalytic converters, converts noxious gases into a nice ones. You can actually sniff up your nose and it won't kill you. That's what they're there for. How do Lambda sensors work? Well, this is the next bit, I'm afraid. So get your cup of tea. In fact, get another cup of tea, because we're going to go through how Lambda sensors work. And I've even done a nice little diagram and an animation for you. I don't do them often, but I've got a lovely animation for this one. Right, let's start with how Lambda sensors, the narrowband sensors, work. Righty-ho, well, it's a material called zirconia, which is actually zirconium dioxide that is doped with other elements. And it's in a thimble shape that pops into the exhaust pipe. Now, if you think of the thimble shape, so the thimble's actually going, the top of the thimble's going into the exhaust pipe. Now, where's the inside of that thimble going? I'll tell you, it's going into the ambient air. So yeah, Lambda sensors have to have ambient air going into one side of them. And if they blocked up, they don't work. So you've got to have ambient air, fresh air coming up through the sensor to one side of the zirconia. Righty-ho. Okay, so we've understood it's the thimble-shaped thing, outside of it in the exhaust, inside of it, ambient air. Okay, the next thing we do is we stick electrodes on it. So you've got one electrode on the outside. It's made out of platinum. This thing only works with platinum, and it's porous, so it's got lots of holes in it. So it allows the oxygen to go through it. And on the inside is another electrode made out of platinum on the inside of the thimble, and it's joined to the ambient air. Rightio, what we're interested in is measuring oxygen. It's only oxygen we're interested in, and what we're interested in is the difference between the oxygen level on the inside and the outside. So ambient air and the oxygen in the exhaust pipe. And you might say, well, isn't all the oxygen gone? It's all been burnt. No, it hasn't. In fact, there's an exact reading of the residual oxygen in the exhaust that has to be maintained for the catalytic converter to work. Now, if you've got too little oxygen, it can't do anything. It gets all clogged up. If it's got too much oxygen, gets too hot, catches fire, melts. So we're interested in the amount of oxygen in the exhaust pipe. Very important. The exhaust still has oxygen in it. It hasn't all been burnt. So if you've got a very lean mixture, it goes pat, and lots of the oxygen is left over, so you get quite a bit of oxygen coming through the exhaust pipe. A very rich mixture, it burns up all the oxygen. There's no oxygen left in the exhaust pipe apart from a tiny residual amount. Get it 14.7 to 1 fuel air mixture and you get a certain amount of oxygen left in the exhaust pipe. Now, zirconia is doped, so it produces a certain voltage when that amount of oxygen compared to the ambient air is left in the exhaust. And at that point, the fuel air mixture is 14.7 to 1, and the catalytic converter is very happy. So a narrowband sensor is designed so that it changes from one voltage to another exactly at the correct residual oxygen level. That's very important. So we're not actually measuring fuel air, we're actually measuring residual oxygen. And we just say, well, at 14.7 to 1, we should have 200 parts per million oxygen atoms going through the exhaust. Well, close enough. So what's happening with this thimble-shaped thing? Well, if you remember your electrical knowledge from school, a battery has got a positive and negative terminal. You put a load on it and electrons move round all the time. It goes through the wire, through the electrolyte, through the wire, through the electrolyte, between the two plates. That's why it's called electrolyte, because it's got electrons going through it all the time. Zirconia works in the same way. It actually produces electricity. You don't get electricity for free. You've got to heat the thing up in the first place. It's got to be beyond 300 degrees centigrade. That's important to know. So the first narrowband sensors, you just had to wait for them. The exhaust will eventually warm them up, and it get up to about 600 degrees C in the exhaust pipe, and then they're working perfectly happily. But of course, people don't want to wait 2 or 3 minutes for the Lambda sensor to warm up. The governments don't want it because the catalytic converter isn't working properly, maybe getting blocked up or caught on fire at this point. So what you have to do is stick 12 volts in it. It's got a heater in it, heats up the zirconia so that it reaches above 300 degrees C, and then it will start working. Got to be above 300 degrees C. Right, let's have a quick look at the animation and I'll go through what's happening. Okay, so that's a standard diagram of a Lambda sensor. There with the sort of voltage coming across it. We'll twiddle it round and put it into our exhaust. So here's the exhaust pipe. That's the ambient air at the bottom. There's the 2 electrodes, positive and negative. Positive goes to the inner platinum electrode. Negative goes to the outer one. Okie doke, so there's your zirconium dioxide, or zirconia as they call it, doped to produce a certain voltage at a certain oxygen transfer. Okay, so in a rich condition, there's much more oxygen in the ambient air. So you get this movement of anions between the ambient air and the exhaust, just like a high pressure going into a low pressure. Okay, so a rich condition has burnt much more of the oxygen than this, which is a lean mixture. And in a lean condition, you get a much smaller amount of anions travelling between the inner electrode and the outer one, so the voltage drops. Okay, so there's your lean condition. When we go rich again, which is what's going to happen, because of course the DME just changes the fuel air mixture quite slightly, and it will change it between a rich condition, which we got now with lots of anions moving across, and a lean condition with much less of them. And that's what's happening all the time. Lean, rich, lean, rich. And you can see the amount of anions is changing, and hence the voltage at the output of the sensor is. And you get that sine wave out of the sensor due to the fact that the DME is changing the fuel air mixture by tiny amounts very quickly. Right, a quick précis on narrow range Lambda sensors. They are there to protect the catalytic converter and to ensure that the environment is protected by trying to change as much nitrous oxide and carbon monoxide to harmless gases, which it does very well. Can only do that at 14.7 to 1 fuel air mixture. Okay, and of course they're 4-wire in BMWs, 2 wires for the sensor itself go off to the DME, 2 wires to a heater, then to the heater relay, which can be switched on and off. And they only work at 300 degrees C, and above normally they'll be up at about 600 degrees C. Error messages for Lambda sensors which are a Lambda fault is open circuit or short circuit for the heater, open circuit or short circuit for the sensor itself. Last one, aging, and that usually means that the Lambda sensor's dirty. It's coked up on the inside where the exhaust is, or it's blocked up where the ambient air goes in. Cleaning them with brake cleaner works. It can get rid of the coke to a certain amount, and there's been many success stories of Lambda sensors that had the aging code that cleaning them with brake cleaner tends to fix them. Problem is getting the things out in the first place. They don't like coming out of the exhaust. They've been there for years and they get pretty much seized in there. So most of the work is removing them or getting the car up far enough so you can get underneath and remove them. You might as well change the sensor while you're there. But those 5 codes are about it for Lambda sensor errors. All other codes are problems elsewhere. Okay, so before we move on to why you get these error codes, let's have a quick look at wideband sensors. Now, wideband Lambda sensors are used in most modern cars, and it allows them to run the mixture richer or leaner than 14.7 to 1. During acceleration, you want the fuel wear to be richer. That removes or reduces the chance of getting detonation. A richer fuel air mixture will not detonate in the same way as a lean one does. That allows you to move the timing fully advanced, get the most power out of the engine. Get the best fuel economy, you can lean out the mixture slightly, and that is what a wideband sensor is for. It can measure the fuel air mixture at other extremes. So when it's richer, it'll just give a voltage output. It's completely linear against the residual oxygen. So as the fuel air mixture richens, it'll go slightly higher, and as it leans, it'll go slightly lower. But it never reaches the extremes of 0.2 and 0.9 of a volt. In fact, the voltages are slightly different on a wideband sensor anyway. As a normal rule, the upstream ones on modern cars are wideband and the downstream ones are quite often narrowband, and that's all that's needed to check if the catalytic converter is still working correctly. Right, now you know absolutely everything about how Lambda sensors work, and a lot you didn't need to know. How does that help you diagnose engine problems? How do you get the information from the Lambda sensor to tell you if the engine is running with the correct fuel air mixture? Well, first of all, in England, or in the UK, every year we have a Ministry of Transport test. They stick a probe up the exhaust pipe. If you've got too much carbon monoxide or too much noxious gases, including hydrocarbons and nitrous oxide, you fail the MOT, you can't drive the car on the road. Now, the same is true in Germany with the TUV, and the same is true in California with the smog test. So you know straight away if you've got fuel air problems. Right, what in a situation where you don't have the tests, or you just want to really know if the engine's got a problem? Maybe it's slightly lumpy at tick over, that's the usual one that gets us. Well, for that you need adaptations. Now, rather than me explain it, I'm going to be talking about adaptations, so I better interject and explain what adaptations are, because they're so important to the correct running of the engine, and the diagnostic pages can tell us so much about how the engine's running. Right, so let's do a quick explanation. We've got a single cylinder engine here. It's slurping in air through the MAF, which is being read by a computer which is up here, and it commands the injector to open for 10 milliseconds per revolution. We haven't got a clue whether the mixture's right or not, because we haven't got a Lambda sensor connected to anything. Okay, so this is now a closed loop, which is what we have in our engines. This is just one of 8 cylinders, and we've got the Lambda sensor, goes through an integrator, I'll mention that later on, and then it goes back to the ECU and it will adjust the injector duration per cycle until it gets it right. Okay, so that's all fine and dandy. What happens when something goes wrong, like we've got a huge leak just after the MAF, and now the MAF's only reading half the air that's going in, the rest of it's coming in through this big hole in the boot. And so the ECU says, well, we've got half a gram of air coming in per revolution, so it's going to be 5 millisecond injector duration, and of course that's much too lean. And the Lambda sensor measures it as being too lean, and it stays too lean. Instead of going too rich, too lean, too rich, too lean, it stays lean. And so what we have is, this is where adaptations come in. And the adaptation is the engine computer says, well, it's been too lean for quite a long time. I'm going to start increasing the injector duration each revolution, or each 10 or 20 revolutions, and see if we can get it back to being the right mixture again. And as it does that, it saves that information into the adaptations. That setting can be used again the next time the car's started. So if we've got a leak, or the math isn't reading correctly, or some other problem, we don't want to be in a situation where we turn the key on the car the next morning and it's still getting it wrong. What we want is information stored that tells it to get the mixture right, and they are what adaptations are. And we have two lots of adaptations, one which is used at idle mainly, and it's additive, adds a bit of fuel each time, so it increases the injector duration each time. And the one's more for cruising, where it multiplies the injector duration by a certain amount, and it should be multiplied by a factor of 1. But if it's slightly lean, it would be 1.01, 1.02, and so on. Thanks very much, Tim. So in a nutshell then, if your engine mixture is too lean, then adaptations will start creeping up to richen up the mixture until the Lambda sensors say that's about right. And if your mixture is too rich, adaptations are going to slowly drop down, go negative, so they reduce the amount of fuel that's been injected in the car until the Lambda sensor's got the correct reading. Fantastic. So that's what adaptations are all about. It's all we needed to know. I don't know why I got earlier Tim to tell you all about it, but we did. Right, now that you know everything you ever need to know about adaptations and Lambda sensors, what good does it do you if you've got a problem with your car and you need to fix it? Well, that's what this section's all about. Section 2, what you do with the adaptation values and where the problem is. Right, well, to get to the first bits we want to look at, little thin screwdriver. Let's be careful with these fellas. They're easy to lose and easy to break and impossible to get. There we go, he's off. Don't forget the cruise control cable if you've got one. There we go. Right, acoustic cover now hasn't been off for, well, probably a couple of years, I should think. So be careful because they tear. Very easy to tear these things. There we go. He's off. Additive adaptation's quite high. Sometimes a lumpy engine, but not usually. And the multiplicative around about normal, round about 0. Okie dokes, that usually means there's a vacuum leak at idle. And that's why multiplicative don't mind too much, because as soon as you open the throttle, the vacuum diminishes in the manifold, and whatever leak you've got between here and all over there doesn't matter so much. Because the usual cause for that is the manifold gaskets. Now, fortunately, we've got a quick fix for the manifold gaskets. Such a simple fix as well. It takes you about half an hour to do. Don't have to take off any more than I've taken off now. Rightio, in the same vein, you can get the high additive ones where you're not measuring all the gases coming into the engine. And that usually means a leak here at the bellows. Now, a bellows might look very nice and shiny, but especially down the back there, they do crack. And then, of course, instead of all the air going through the MAF, half of it comes in through a leak. That puts your additive adaptations positive as well. And again, it doesn't make much difference to the multiplicative, because in that situation you're dragging through a lot of air, and compared to the small amount that's coming in through a cracked bellows, it doesn't really matter too much. Smoke tests, that's quite often okay to do, but it generally doesn't find the problems between the MAF and the throttle body, because you don't want to smoke test the MAF. Doesn't do them any good. So smoke test good, push in air as much as you can and see if it comes out of the manifold gaskets. Now, It isn't just manifold gaskets. On the early cars, like our E31, E32, E34, 36, 38, 39, there's all sorts of rubber bungs. they just perish and fall off. And here's a picture of one. I'd actually changed it about 5 or 6 years before, and I thought I'd just check it. Yeah, it's a huge split in it. So that's letting in unmetered airs. Adaptations have gone positive by quite a lot. And that's one of the caps there. You can see it with the yellow band. You pull the yellow band out and that cap will come off. That's one of them that can leak. There's a big one to the right there. You can see it sticking out the side of the PCV. On the E38s, 39s, that is a vacuum takeoff for the brake booster. On the E31s, and I can't remember on the E30, yeah, the E32 is the same. That isn't a vacuum takeoff, so that's capped as well. Get that to leak and you've got big problems. It will let in unmetered air. So yeah, that's another one which causes high additive adaptations, where it's trying to compensate for the air which isn't being metered and just getting straight into the manifold through those connections. So yeah, there's the rubber bungs on the back of the pressure control valve, the PCV at the back of the manifold. For Germany, and only Germany, although the residual effect is on cars throughout the world, is that it's got this T-junction that goes from the canister to the fuel tank ventilation valve, to a little solenoid, which then goes into the inlet manifold. It is there, this T-junction is there, and it's got a little cap on it as well. Why has it got a cap on it? It's because that is a place where in Germany, to pass the TUV test, the smog test in America and the MOT in the UK, they had to allow a certain amount of unmetered air into the manifold. That's what the T-junction was for. They'd pull off the rubber cup and get unmetered air, and they'd expect to see the operation of the engine change and for it to compensate for it, because it only allows a certain amount in, and you'd get adaptations of plus 20, plus 15, somewhere around that, and they'd say, yep, the engine, the DME, is changing the injector duration because of this air leak. And then they put the bung on, give it a big tick in the box. Unfortunately, the rubber bungs are exactly the same as the ones on the back of the manifold. They rot and they drop off. And also, of course, if you've got leaks elsewhere in the same system, you get the same problem. Right, one rubber bung I forgot to mention at all is the one we're staring at now. And you think, where's that then? Oh, I'm going to zoom you out. Here we go. Going up and out. There we go. It's actually on the throttle body. And yeah, that's another rubber bung, just the same as all the others. I have replaced that. I replaced all the rubber bungs at one point. But yeah, that's one is worth mentioning. That's a good place to get a vacuum leak. The early cars are full of rubber bungs everywhere that perish and drop off. Now, if the air leaks are bad enough, for instance, the big bung at the back of the engine, that'll give you, the adaptations will keep on going positive and positive until it gives up. Has a go at putting the multiplicative up as well to help out when it's run out of the additive adaptation. So you end up with very high additive adaptations and reasonably high multiplicative. That's always a great sign of a vacuum leak, any part of the car. So seals at the bottom of the manifold, all the bungs on the back of the PCV and the lines which go to the brake booster on the E38 and E39, you get a leak in that, so a one-way valve, and you get the same problem. PCV valve at the back is a classic. Get a torn diaphragm in a PCV, you're going to get a Lambda sensor error, absolutely no doubt about it. They let in so much air, car misfires and stumbles at idle. They usually go all right when you're getting on a bit, put a bit of acceleration on, not too bad. Idle, hardly ever idles. Okay, so positive adaptations, you've got an air leak. And if the air leak or vacuum leak, if it gets to a certain point, then you'll get a Lambda sensor error. But what you do, diagnostics, IMPA, adaptations, they're very positive. I've probably got a vacuum leak. Now, if your fuel pressure is wrong, then the adaptations are going to change quite considerably. Now, we talked about how the fuel air mixture has to be richer when you're accelerating, and it has to be richer even if you've got a narrow band sensor. Let's forget about wideband at the moment. With a narrow band, you need a much richer fuel-air mixture. What does the Lambda sensor do during this acceleration phase? Nothing. It completely ignores. DME says, no, I haven't got a Lambda sensor. I've forgotten all about them. Now, of course, the DME to a certain extent is blind when you want to richen the mixture, because, of course, the Lambda sensor can't measure a richer mixture than 14.7 to 1. So what happens when you accelerate? Well, with the V8s, and I think it's the same for the straight 6s and so on, they all have a fuel pressure regulator that regulates the fuel pressure at the injectors, and at idle and cruising it's around about 3 bar or so, and that gives the right pressure at the injectors, and the DME knows that if it opens the injectors for a certain period of time, then you get 14.7 to 1. Now, the fuel pressure regulator is a two-stage one, actually. It can either be 3 bar when you're idling or 3.5 when you're accelerating. And the way it does this, it has a little vacuum tube that goes to the manifold. In fact, it goes to the back of the pressure control valve, or PCV, at the back of the inlet manifold. Now, when you're idling or very light cruising, the inlet manifold vacuum is quite great, quite a depression in there. And what that does is it's got the pipe that goes to the fuel pressure regulator, it slurps the diaphragm and it reduces the fuel pressure. So that's the normal situation. You've got 3 bar of fuel pressure at the injectors, and so the DME knows if it opens it by 0.2 of a millisecond, then you get the correct fuel-air mixture. Now, when you put your foot down, the vacuum decreases to the fuel regulator. It puts the fuel pressure up to 3.5 bar. Now, that's been calculated to give the correct rich fuel mixture when you're accelerating, and it's as simple as that. It's a fuel pressure regulator, 3 bar or 3.5, idling or when accelerating. Simple as that. So that's such a simple way to increase the fuel pressure when you're accelerating. As I said, the DME is completely blind to it, hasn't got a clue what's going on, because the Lambda sensor, it just isn't doing anything. Now, if you had a wideband sensor, you could have measured it, but they weren't invented into about 1989, which is too late for the E31, E32s, E38s, and so on. So, yeah, narrow band, simple way of enriching the mixture with a fuel pressure regulator. Okie dokie. Now, during that period, of course, the Lambda sensor's not doing anything. Adaptations aren't changing in the slightest. Now, from much younger Timm, who explained how adaptations work, this gives us the clues to what's going on. Now, with adaptations, if the fuel mixture, say the fuel regulator got stuck at 3.5 bar, DME will say, right, we need to adjust adaptations, or do it -1. Is it lean enough yet? No. -2. No. -3. No. -20. Well, that's as far as I can go. I can't adjust it anymore. Something's horribly wrong. Of course, the fuel pressure regulator's got stuck at 3.5 bar. That's when you get a Lambda error. It says Lambda range insufficient, i.e. adaptations have reached their limits. I can't do any more, mate. I've given up. So it makes it as lean as it can, but it can't do that. And you get that error warning. The reason you get that error warning, and it's an important warning, means your catalytic converter's failing, and it also means that the catalytic converter can't convert the noxious gases. So 2 things are happening. You're setting fire to your catalytic converter, we're blocking it up, and you're bunging out noxious gases. But DME has done all it can. It's made the mixture as lean as it could, and it wasn't good enough. So in that sort of situation, if you've got a big minus numbers in your adaptations, in the additive ones, down to -20, -30, you can be sure that you've got fuel pressure problem, or an injector that's stuck on, or a fuel pressure regulator that's leaking fuel into the manifold, which they quite often do because they've got a diaphragm in them. There's a deep vacuum in the manifold, and so it's just slurping raw fuel through the pressure regulator. So it's no wonder it can't get the fuel-air mixture right. So adaptations at -20 or -30, the additive ones, fuel pressure problem, diaphragm burst on the fuel pressure regulator, an injector stuck open. So they're pretty straightforward, and they're usually quite easy to find by measuring the fuel pressure regulator. Now, where you get high additive adaptations on one bank and not the other, that's usually due to a misfire. Now, if you think about it, of course, you've got a misfire in one cylinder, cylinder number 1, for instance. Got the other cylinders, 2, 3 and 4, are firing normally, and they'll be producing the residual oxygen at an expected level. Whereas cylinder 1 is misfiring, hardly burning any fuel, and that leaves a lot of oxygen left over. So on that bank, the Lambda sensor is saying, well, the residual oxygen seems a little high. I need to richen the mixture to get it back to the right place. So adaptations start clicking up, clicking up, clicking up. And at one point it will say, well, adaptations at limits, Lambda error. And that's because you've just got fresh air going through a cylinder. Now, in that sort of situation, using diagnostics, you're usually okay. You've got one bank that's firing normally, one bank that you've got one cylinder on which isn't firing normally. Look at the smoothness or roughness page of IMPA, and it will tell you straight away which cylinder it is. Now, when they're not firing at all, I say you've got an injector that's blocked or something like that, then it's going to let you know. But where it's misfiring, then smoothness or roughness will show you which cylinder is causing the problem. And then you can just devote your time to that one, trying to find out what the reason is. It could be the coilover plug unit, it could be the spark plug itself. Could be an injector problem, though. If you haven't had the injectors out on these cars, don't take them out. Just use injector cleaner in the tank now and again, and it keeps them in perfect, good working order. Generally, what happens is people take the things out, they either break the plastic of them, they tear the O-ring, replace the O-ring, and it all curls up on its way back in again, because they haven't used any grease. It's a hiding to nothing. The injectors last forever on these, unless the car's been sitting for 4 or 5 years, in which case they get all blocked up. But on a normal running car like this, leave the injectors alone. They don't want to be fiddled with. So that situation, high additive adaptations on one bank, normal on the other, very likely to be a misfire. How you find it, roughness or smoothness in IMPA will tell you which cylinder is causing the problem. Right, we have a third situation with adaptations, which is quite strange, which is where you have one bank has really high adaptations, both the additive and the multiplicative, whereas the other bank, it's really low, so have really low additive and very low multiplicative. What's going on there? Especially as you've only got one math to actually read the air coming in. How can you ever have a situation where one bank is lean, the other one's rich? Well, there's a very good reason for that here, and it's one I've come across personally in this car, and that is a failing catalytic converter. Now, when catalytic converters start to fail, they do one of two things. They either break up to end up in being shards of honeycomb, or they melt and then they just block up the exhaust. Now, as I say, we've got one MAF, of course, but 2 Lambda sensors. So you've only got a certain amount of air going into the car, and then each bank has to decide how much fuel to push into the engine. Now, in a situation where you've got a blocked catalytic converter, the one that's melted, you don't get much exhaust through there, and because you don't get much coming out, you don't get much coming in either. So what's happening there? Let's say the left-hand catalytic converter is blocked up. Well, most of the exhaust gases are going through the right-hand side, and that then means that most of the air's going through the right-hand side. So in that sort of situation, quite often what happens is you end up with a right bank that's too lean, hence the positive adaptations on the right-hand bank, and the left-hand bank, which is blocked, much too rich, because it's getting very little air through, and it's still putting about the same amount of fuel into it. So you end up with one bank that's very lean, one bank that's very rich. A sure sign that you've got an exhaust blockage, which could be at the catalytic converters, they usually are, or anywhere in the exhaust system. Say you've run over something and it's actually compressed some part of the exhaust system. So if you've got positive on one bank, negative on the other, first thing you always think of is the exhaust, whether it's the cats or some other problem. Now, in another situation with catalytic converters that fail, I told you we can have a blocked up one where they've overheated, or we have one that falls apart. And in fact, in my car, even though I had one which was failing, and there's a good reason for that, it was the other side, the right-hand bank, that was failed and had broken up. And what happened then is everything's fine while you're driving along normally, but when you put your foot down, a bit of that honeycomb rattles its way and blots up the exhaust from the catalytic converter. And that just stops all of the exhaust getting through that bank completely. And immediately what happens is you go on to just one bank, you go on to the left-hand bank. Right-hand bank can't do anything, it's not getting any exhaust through. The strange thing about this problem is that if you actually stop the engine, turn it off and restart it, it will quite often run perfectly normal until you stick your foot flat on the throttle again. And what happens is, because of the conical shape of the ends of the catalytic converters, the bit of honeycomb that's gone into the exhaust outlet just drops back into the catalytic converter body again, and everything's fine. And it's only until you start putting huge amount of exhaust gases through the catalytic converter, honeycomb moves around, blocks up the exhaust. So yeah, positive on one bank, negative on the other, usually by quite an amount as well. Exhaust system somewhere. Maths. You would have thought, well, the math could be a problem, couldn't it? It might be mismeasuring the air. They generally don't at idle, which is very strange, I've always found. They do it more when you're accelerating. The DME can compensate for a math that fails completely. Not a problem at all. It uses the other sensors, it uses the throttle opening position sensor and all sorts of other sensors, the temperature sensors and things like that. And it'll get the fuel-air mixture more or less right. If you get one that's mismeasuring, and they generally mismeasure at high throttle levels, then you'll start getting multiplicative errors. You'll get your additive errors will be small, 10, 15, multiplicative up to ×2, I've seen some of them. That is generally the math. You also notice it as well. I had this on my E32. Idle's perfectly all right. Put your foot down. Yeah, not enough power, nowhere near enough power. The DME can't notice it. Now, the MAF is a primary sensor, and so it takes it as gospel that that's the amount of air coming into the car, and it adjusts the injector dwell to suit that. Now, of course, as we remember from all my blurb, about half an hour ago, you don't use Lambda sensors when you're accelerating. So the DME's got no idea that something's gone wrong, but if you've got a lack of acceleration and multiplicative starting to increase, then that's going to be the math, much more likely to be the math than anything else. Fuel pressure might have something to do with it, but if you've got a fuel pressure problem, then both the multiplicative and the additive go up by reasonable amounts. So you know, for instance, if they're both up, yeah, that's fuel pressure problem. Just the additive one's going up, vacuum leak, injector stuck open, something like that. Multiplicative going up, yeah, that's probably the math. Or in fact going down, I've seen them do that as well. They don't measure the air properly, and without the Lambda sensor to adjust it, then the math is the problem. Maths are horrendously expensive for these old cars, but you've got to use the OEM ones because the replacement ones don't work. Now, this was my advice 20 years ago, and I went against my advice once. I thought, oh, surely one of these ones from eBay, got to work, hasn't it? No, it didn't. It wasn't too bad on acceleration. I'll give it that. It was a lot better. When it's warm, it just didn't measure the fuel air mixture, the amount of air coming into the engine properly, and you couldn't start the car. It would just start and misfire and stop again. So yeah, Chinese maths, thumbs down for me. OEM maths, 300 quid, 400 quid or so. It's probably around 400 quid for an E31 and E32 now for the V8s. All this advice, by the way, is relevant for any size engine. So it can be the V12, can be the V8s, can be the straight six, even the 4 pots. It's the same situation. It has DME and adaptations. Okay, so have we covered all the errors we can get from the Lambda sensor? Yeah, more or less. Right, part 3 at last. This is for people who know how to get the adaptations and the roughness from using IMPA or any other diagnostic problem that supports those functions. And you've got a Lambda error. First of all, number one, we'll quickly wipe from the slate the real Lambda errors, and there's 5 of them. Open or short circuit for the heater, open or short circuit for the sensor, aging. Now, if you've got aging, that's usually due to soot on the tip of the Lambda sensors or blocked up from underneath because they need ambient air going into them. They can be fixed using brake cleaner. It works quite effectively. However, 99% of the effort is getting the blooming things out in the first place, either up on a lift or on a pair of ramps if you really have to. Yeah, they're seized in there. They don't want to come out. So by the time you spent that much effort, change the Lambda sensors and save you a lot of time. Now, if you buy a universal one, then you're going to have to be cutting and joining wires and make sure you get the right colours as well, because the colours on the universal sensor aren't the same as BMW's. So if you buy an OEM BMW Lambda sensor, then they just connect straight in, no problem at all. Okay, so that's got rid of those, the 5 real Lambda error faults. Okie dokes. Now we move on to the second section, which is of this part, which is problems, mechanical problems that cause Lambda error faults. And we'll start with the simple ones, and that's where positive adaptations, the additive ones are starting to go high, and the multiplicative are starting to follow it. That's a vacuum leak. Now, it could be on many places of the engine. You get a very high leak, and that's always the PCV valve, then it'll trip a Lambda error fault. If you've got just winding up slowly ones, then yeah, vacuum leak elsewhere. PCV valve is usually the cause for this, and you get a howling from the back of the engine because the diaphragm in the PCV valve has torn and it's letting fresh air through to the manifold. And because so much fresh air is going in there, at idle, you hear it straight away, a really loud hissing noise or a howling from the back of the engine. The other errors which just cause the additive to increase slowly, then yeah, vacuum leak elsewhere. Rubber bungs on the back of the PCV valve. We've got 2 on the E31, just 1 on the E38s and E39s, and that's because they use one of the takeoffs for the vacuum boost or for the brakes. Then you've got the bungs at the front of the engine. On E31 you've got 2, you've got 1 on the throttle body and 1 on the T-piece. So all of those bungs, they do get old, they do drop off, they cause the problem. Could obviously have a manifold leak itself. Now use my 5-minute fix to do that, and that'll get rid of those problems. I've never had the manifold off of my E31. It's 25 years old. I've used the 5-minute fix for the manifold, never had a problem since. So yeah, that's where both adaptations are starting to creep up. PCV valve, vacuum leak, things like that. Okay, so where you get one bank starting to creep up and the other one staying perfectly normal, usually a misfire, and you'll notice it at idle anyway because the engine will be slightly lumpy. So yep, either a single or a double cylinder misfire, and I say double because the manifold gaskets serve 2 cylinders, 2 adjacent cylinders, so you've got 4 manifold gaskets around. If it's a pair of them, and you'll find that out on the roughness or smoothness page of IMPA, that will tell you which cylinders are causing the problem. Then if it's a pair of adjacent cylinders, it's probably the manifold gasket. Again, 5-minute fix for that will sort out all of those problems. If it's still a single cylinder misfire, then yeah, coil over plug unit might be fizzling out. Or of course the classic, which is oil down the spark plug holes, because we do get valve cover leaks and the oil does tend to end up in the spark plug wells, and eventually the oil rises to a point where it starts to mess up the rubber boots. They go a bit floppy and then you get sparks down the side of them. Now people always say, well, oil is an insulator. Yeah, clean oil is, dirty oil isn't. So yeah, oil in the spark plug wells will cause a single cylinder misfire, as will a coil over plug unit. Unfortunately, we get really bad shorting down the side of the spark plug. It can damage the coil over plug unit. Okay, so single, double cylinder errors will cause one bank to go high and the other to stay where it is. Rightio, number 3, which is caused by catalytic problems. That's where you get one bank goes really high, one bank goes really low, causes a Lambda error. You've got one catalytic converter that's blocked up. Most of the air is going through the other bank and it ends up being lean. The one with less air going through, because if you can't get exhaust out, you can't get air in, simple as that, it gets a lot richer. So you've got one rich, one lean side. And it's usually the rich side, is it the rich side that is high? Yeah, the rich side is the one which has got the catalytic converter that's blocked. Obviously, you change them in pairs, they've got to be balanced anyway. Catalytic converters will last you about 20, 21, 22 years. You've got an engine problem like the vacuum leaks, they don't last as long because it gets the mixture wrong, and that will cause them to fail quicker. But yeah, catalytic converters, one will block up, or in my case, one will block up, the other one could just completely disintegrate. So very skewed adaptations. Yeah, lack of air going through one bank, and that will be due to a blocked up catalytic converter. Right, number 4, and hopefully the last one. This is where you've got adaptations very low, got a Lambda error fault, multiplicative and additive are dropping through the floor. That is a fuel pressure problem. Now, as I said earlier, we have a fuel regulator on these cars, which runs, well, the early cars runs at either 3 or 3.5 bar. When you're idling, it will be at 3 bar. But if you have problems with that regulator or the vacuum isn't reaching it, then at idle, you can get 3.5 bar. Adaptations have got no way of compensating for that, so they drop down to the floor along with the multiplicative. You can smell petrol in the exhaust and all the rest of it. Yet your fuel regulator is now stuck at 3.5 bar. Also worth saying, because we have a fuel system that circulates the fuel all the time, you have got a blockage in the return to the tank. That gives the same problem. Fuel pressure goes really high. Now, the indication is, of course, multiplicative and additive very, very low. Tried the best they can to lean out the mixture, generally don't make it. And that will then be most likely the fuel pressure regulator. And although IMPA helped you to this point, you're going to need a fuel pressure gauge to check it. You can check it on the lines anywhere from the fuel tank to the fuel pressure regulator. The pressure's the same there. Don't try and check it in the return line, doesn't make any sense at all. So if you haven't got 3 bar at idle, you've got 3.5, that's most likely the little vacuum tube that runs off the PCV to the regulator. So yeah, that's one where the additive and multiplicative are down to the floor. And that really covers just about all of them. We do get some strange ones now and again where bits drop off and cause some strange adaptations. For instance, where you've got a burnt exhaust valve, that causes problems on one bank. Very difficult to find. I'm afraid a compression test is the only way to go on that one. Yeah, if you've got all the way through all of this video and you still haven't sorted out the problem, yeah, check your compression on all 8 cylinders and that'll tell you which one's got the problem. Another one which I've seen is where you've got adaptations very strange on one bank and not the other after timing change replacement, and usually the VANOS and all the rest of it on the TUB engines. Now, even where you haven't got the TUB, so you've just got a straight M62, if you get the timing wrong, that affects the fuel air mixture because it uses the spark ends up in the right place, but unfortunately putting the fuel in doesn't. And so in that situation, you either end up with much too rich or much too lean mixture. Yeah, that is a bit of a problem. However, it does help you with a compression test because the same problem with getting the fuel into the engine and the air into the engine means that the compression is going to be lower. So, and in some cases higher because it's too far advanced. So if you've got one bank that's got normal compression test readings and the other one that hasn't, I'm afraid that's going to be timing. And I've seen this so many times recently because everyone's changing their timing chains and the guides and all the rest of it and the VANOS units. And unfortunately, the adaptations end up miles out on one bank. and the compression test shows either much higher or much lower readings. Right, you've got the timing wrong. Yeah, it's a pain in the neck, so it all has to come apart again. Yeah, sorry to end up off the sour note. Okay, so here we are about 40 minutes later. Well, I'll try and edit down a bit, but I don't think I've got much luck. We now know what adaptations mean, how they affect the engine running, what problems they point out, how Lambda sensors work, what they're introduced for, how the catalytic converter does the conversion, and how important it is to get the correct residual oxygen level so that it can do its conversion, because it won't do it if the residual oxygen is either too high or too low. And that, of course, the byproduct is the fuel air mixture is either too rich or too lean. So using that information, we can diagnose the problem, adaptations, roughness, we can find out everything. Right, well, if you sort of managed to hang on to the end of the video, thumbs up to you. It was a difficult one to go through, difficult one to record as well. And I'm glad you stayed with me. Yep, subscribe if you haven't, put a thumbs up, and I'll see you in the next one.